No? Okay, good. So in which case then, there's two things left to do. We need to talk about the expectation and we need to talk about the variance. That's what we always do with random variables, yeah? We find the probability mass function. We've done that, okay? Did anybody actually follow the things through the slides, sort of derivation of where it came from? Yeah, it literally just comes from a binomial distribution and just considering it as you consider more cases. Yeah, it's literally where it comes from, okay? But yeah, if you don't want to worry about that, there it is, okay? We also need to look at the expectation and the variance as well, okay? So, what do you think the expectation should be? So if I give you a random variable, can I clear this off the board or are people still copying? Can I clear it? Yeah. Okay, good. So let's just remind ourselves of our random variable notation for a Poisson distribution. So we have x is distributed using a Poisson distribution with some rate lambda, okay? So let's suppose, I think we did it on Wednesday, didn't we, with the heart rate, yeah? We said that, I think Nikki, your heart rate was like 13 beats in 10 seconds or something. So we said, okay, if x is the number of heartbeats in 10-second period, okay, of course we assumed it was resting heart rate. Then we had like x was distributed using a Poisson distribution with a rate of 13 heart rates, okay? What do you reckon the expectation of x would be? What do you reckon the expectation would be? So given this, given that the number of heartbeats in 10 seconds was 13, why is it going to be 13? What does expectation literally mean? Sorry? It is related to mean, absolutely, yeah? If you like, it's the average. If you look at any 10-second period, how many heart rates do you expect to get? That's literally what expectation means, yeah? So given how we defined our random variable, that thing there literally means the rate. Says in an average 10-second period, you would get 13 heart rates, or 13 heartbeats. You would expect the expectation to be the same as that rate, okay? So would you be happy that in general, the expectation, in fact, let me write it over here, so we've got a nice little sort of library going on. The expectation of this random variable should just simply be the same as the rate, okay? Good. And you can see that as well from the probability mass function graph, yeah? The one with the highest probability, in other words, the bar with the highest height, is going to be your expectation, yeah, which is lambda. Okay.
Here it looks like there's two.
It does in this case. Now, in reality, they're not. It's just because I've decided to truncate them at 4 decimal places. Okay. If I let it run, eventually this one would come out as a slightly higher probability. It's a really good point. And then, of course, the idea is, you've seen this kind of shape before, as you consider values away from the mean, so either to the right or to the left, the probability should decrease. Yeah, same as in binomial, and we'll meet this shape again when we look at normal. Is this okay? Good, fantastic. So, am I going to take you through the proof? No, you can go through that in your own time. Okay. So again, if you just wanted it to be proved properly, then you can prove that the expectation of a Poisson distribution is equal to lambda. And there's the proof on the board. Okay, it's just simply considering a bit of Taylor series and stuff like that. Now, by the way, just because this looks a bit complicated, you go, how did I get from here to e to the lambda? So how is that series? So in other words, the sum of like 1 plus lambda over 1 factorial plus lambda squared over 2 factorial. So how do you get that to e to the lambda? Don't worry, it will come clear, well, about 6-7 weeks time, I guess, when we do it. Yeah. But for the moment, just kind of accept it to be true. Okay, good. Okay. Now what about variance? What about variance? So we can think about variance like this. Okay. So have a look at what I've got on the screen. I've simply written out the formula which I know for variance. It's e of x squared minus e of x all squared. So you notice what I've done here is a little cheat. I've literally taken away the expectation, but then immediately added it again. So effectively, that line and that line is exactly the same. Would you be happy with that? Okay. So now where am I going to go with this? Well, have a look. Have a look at that next line. Can anybody tell me how I've managed to get from line 2 to line 3? What have I done? So if I write down the board as well to help. So I said...
Add a 0 to the formula. Add a 0.
Okay, so you mean the bit in pink?
Yes.
Effectively, it's nothing, right? Because I'm taking away an expectation, then immediately adding it again. It's gone, right? Absolutely. So at the moment, I've got e of x squared minus e of x all squared is variance. So I can say, okay, well, what if I take away an expectation, but then immediately add it again? Okay? Should in theory be allowed, right? Because technically, I'm not changing the formula at all. Okay? But can anybody tell me how I get from this line to the bottom line on the screen there? Good, factorising. Tell me a bit more. Good, so you've literally said, if I look at these two things, I know with my expectation algebra, if I have e of, I don't know, y plus z, that should be equal to the e of y plus e of z, right? Same kind of idea here. If I look at that bit here, I know going backwards, this should be equal to the expectation of x squared minus x, absolutely. And I've still got this stuff here. Is that okay?
Yes.
And you notice in here, I can do a bit of factorisation. Notice there's an x common to both of them. So I get the expectation of x. X minus 1. Like that, and then like that. Good. Minus e of x all squared. And you're like, okay, so why is that useful? Why is that useful? Well, have a look. What do you think this thing is going to be equal to? So I've kind of put the answer there on the screen. Yeah? Would you be happy using the definition of expectation in order to work out the expectation of a random variable? Maybe if I change that to y to make it less confusing. Okay, this is going to be equal to the sum of y times the probability that it's going to occur. That makes sense? We've looked at that before. Yeah, that makes sense. Okay, so therefore, if I want the expectation of x times by x minus 1, would you be happy this will be equal to the sum of x times x minus 1 times the probability of occurring?
Yes.
Yep. All happy with that? Good. Okay. Now you notice that I already have the definition for probability. Okay? The probability that something's going to occur for a Poisson distribution, remember, is equal to this thing up here. It's the probability mass function. Do you see that?
Yes.
Okay. So now, if I do just a little bit of rearranging, okay, I can say that this is going to be true. Okay, this is going to be true. Just simply by considering the definition of a factorial. Okay? So if I have x factorial, that's going to be x times by x minus 1 times by x minus 2 factorial. So the x minus 1's cancel. So effectively, I'm just left with x times by this thing. Does that make sense?
Yeah.
Good, okay. Sorry, the x's are going to cancel as well, aren't they? Yeah, so I'm just going to be left with that over x minus 2 factorial. And so therefore, this all follows through. I get that. And it's literally exactly the same thing as I had before. Okay? So in other words, I'm literally saying, let me say that again. Okay? I'm literally saying that because this thing here is going to be equal to lambda squared. Okay, that thing there is going to be equal to lambda squared. I've just done it on the board. This thing here is just lambda. And this thing here is also going to be lambda, but squared. Yeah? Lambda squareds cancel. So therefore, the entire thing is just going to be equal to lambda. Okay? So the variance of the variance of a Poisson distribution, simply just lambda. Okay? Now, if you didn't follow that, it doesn't matter, because this is all you need. Now, I say it doesn't matter. Kind of true, kind of not true. Okay? I always have the attitude that I'm trying to train you up to be mathematicians or statisticians. Okay? Being a good mathematician, being a good statistician is not just being about remembering the formulas. Being a good mathematician, being a good statistician is actually having a handle on understanding where things come from. Okay? Getting from here to here is all very well and good. But if you don't know why you get from here to here, you're not really being a proper mathematician. Okay? Mathematicians and statisticians are exactly the same, are all about questioning why. Why does something make sense? Yeah? And if you're not interested in how you get from here to here, you're not being a mathematician, you're not being a statistician. Okay? You need to constantly be questioning, why does that make sense? So all the stuff on the board, okay, I promise you isn't difficult if you just sit down for an hour and just try and think it through for yourself. But the act of actually sitting down and thinking about it for an hour will make you a better statistician, will make you a better mathematician. I promise you. Okay? So even though you don't need it, like I'm not necessarily turning around to you now and say, can you prove that and that, so the expectation of a Poisson distribution is lambda, I'm not expecting you to be able to do that. But what I am expecting you to do is to go away and try and say, I can kind of see how these dots are connected now. Yeah? Make sense? Good, fantastic.